In number 24, we have to write the balanced net ionic equations and identify the spectator ions. These are precipitation reactions, so we've got soluble ionic compounds, and we're looking for a solid to drop out. So when I have chromium 3 sulfate reacting with ammonium carbonate, I look at the rules for carbonate and sulfate, and most carbonates are insoluble, and chromium carbonate isn't an exception. So this will drop out. I put the 3 in there to balance. So I have 6 ammoniums going in, 6 coming out, 3 sulfates, and I get chromium 3 carbonate dropping out of solution. All right, so what are the spectators here? Well, ammonium ion is always going to be a spectator ion, and in this case, the sulfate's going to be a spectator. So when the chromium ion finds the carbonate ion, they drop out and form a solid, and the ammonium ions and the sulfate ions are left behind. That's what it means to be a spectator ion. You're not involved in the reaction. So we leave them out. 2 moles of chromium 3 ion reacting with 3 moles of carbonate to form 1 mole of chromium carbonate solid. A net ionic equation. All right, B. Will barium nitrate precipitate potassium sulfate? Yes. Barium sulfate is one of our exceptions. So barium sulfate will precipitate. So what are the spectator ions? Well, everything's separated before the reaction starts. When the sulfate ion finds the barium ion, they're the one that drop out. So again, it's the potassium ion and the nitrate ion that are the spectators. They're not involved in the reaction. And you can see with precipitation reactions, it's pretty easy. I mean, if the one product is the solid being formed, the other product is the set of spectator ions. They're not a set of spectator ions in the molecular formula, in the molecular equation. So get rid of them, right? Write the net ionic equation. The potassium ions and the nitrate ions aren't involved in this reaction. All right, problem C. Will iron 2 nitrate precipitate with potassium hydroxide? If you look at your solubility rules, most hydroxides are insoluble. Iron 2 hydroxide is no exception. So we balance, and we recognize that it's the iron 2 hydroxide that's going to drop out. So again, when the hydroxides find the iron 2, they drop out and form the solid, and the potassium ions and the nitrate ions go in the same way they come out. They're spectators. So we omit them from the net ionic equation, and we have 1 mole of iron 2 reacting with 2 moles of hydroxide to form 1 mole of iron 2 hydroxide solid. So that's precipitation chemistry. You look at the rules and you predict what the solid's going to be, and you omit the spectator ions. Classify each of the following substances as a non-electrolyte, weak electrolyte, or strong electrolyte. All right, so we did this earlier with the molecules. H2SO3 is sulfurous acid. That's one of our acids, but it's not one of our strong acids. So it's going to be a weak electrolyte. Ethanol is not an acid. I'm sorry. We were going to do a demonstration here. We are going to put the recognize that when we put the sulfurous acid in the water, the reason it's a weak electrolyte is because we get incomplete ionization. Most of the sulfurous acids don't ionize. Only a little bit of ion in the water to light the light bulb a little bit. When I put ethanol in the water, it's not going to light the light bulb at all. There is no ionization. So the H does not pop off the O, and there are extremely small trace amounts of ion in there, not enough to light the light bulb. A non-electrolyte. Ammonium in water will form ammonium hydroxide. That's a Very non-spontaneous reaction, meaning you're not going to make a lot of the ammonium ion and the hydroxide ion. It's not going to go very far forward. As soon as the ammonium ion and the hydroxide ion find each other, they reform ammonia and water. So this is a reversible reaction. Makes it a weak electrolyte. Whereas aqueous potassium chlorate, anything with the potassium ion soluble, anything with the chloride ion soluble. So this goes in, so potassium chlorate dissolves in water. This goes forward, and we get a lot of ion in the water, so a strong electrolyte. Same with copper 2 nitrate. Complete ionization gives you, I'm sorry, not complete ionization. Dissolves in water, right? You get a lot of it to go in the water, so you get a lot of ions in the water. So soluble. Soluble ionic compounds and strong acids are strong electrolytes, meaning when you put them in water, you get a lot of ions. All right, with problem 39, we get a different kind of chemical reaction. In this chapter, you categorize chemical reactions in 3 ways. Either you fall under the heading of precipitation reaction, where we have 2 soluble ionic compounds forming an insoluble one, or you fall under the heading of an acid-base reaction, which is a H plus transfer reaction, or you fall under the heading of a redox reaction, where we have an electron transfer reaction. All right, so A, B, and C here are examples of acid-base reactions. Hydrobromic reacting with hydroxide, perchloric acid reacting with hydroxide, and nitric acid reacting with hydroxide. Hydroxide is the base here. All right, it's matched up with a cation that is either locked in with a solid or aqueous. So looking at the first one, we have 2 aqueous compounds. The H gets transferred from the hydrobromic acid to the calcium hydroxide to form water. All right, so the H goes on the hydroxide, and now you get H2O. Calcium ion and the bromide ion are the cation and the anion left over. All right, so we balance this, right? You've got 2 hydroxides. You'd need 2 hydrobromic acids to react with those 2 hydroxides. So everybody sees the OH. The OH is the hydroxide. That's the thing that's going to take the H from hydrobromic acid. Well, not exactly take it, because hydrobromic acid is a strong acid, right? That H is already detached. It's floating around in the water. And that H plus attaches itself to the hydroxide to form water. So that's the reaction here, right? The bromide ion and the calcium ion go in the same way they come out. They were aqueous at the beginning, aqueous at the end. They're not part of the reaction. This reaction is about H plus ions attaching themselves to hydroxides to form water. And we put in lowest terms. All right, so 1 mole of H plus reacting with 1 mole of hydroxide to form 1 mole of water is the net ionic equation for this reaction. Different with this reaction, right? Copper hydroxide is an insoluble ionic compound. So when the H pluses from the perchloric acid react with the hydroxide, you're pulling that solid apart to make aqueous copper 2 perchlorate. So again, you've got 2 moles of hydroxide for every copper 2 hydroxide, so you need 2 moles of the perchloric acid to neutralize it. So when I look at the complete ionic equation for this, again, perchloric acid is a strong acid. That H is detached. And they go after the hydroxides in the solid, react with them to form water, and copper 2 is liberated during this reaction. Perchlorate's the only spectator ion here, right? Copper 2 is locked up in a solid at the beginning of the reaction, and at the end it's aqueous. So if we omit that spectator ion, it's these H pluses reacting with hydroxides in the solid to form water and copper 2 ion. So here's a picture of it. All right, so there's the solid there, and you've got the hydroxides in the crystal. The H pluses react with those and pull the crystal apart. And copper 2 is now in the aqueous phase. It was locked up in a solid, now it's aqueous. And notice, the perchlorates weren't involved. They went in the same way they came out. It's the same type of reaction with C. You've got nitric acid, a strong acid, reacting with aluminum hydroxide to form water. So you've got 3 hydroxides in 1 mole of aluminum hydroxide. Therefore, we need 3 nitric acids to make 3 waters. So 3 H pluses matched up with the 3 hydroxides makes 3 waters, and you're left with aluminum nitrate. And in the same way as the last reaction, right, you had a insoluble solid aluminum hydroxide, and the H pluses took that apart to release the aluminum ion, and the only spectator in the reaction being the nitrate ion. So when I omit the nitrate, the Nadanik equation for this is 3 moles of H plus reacting with 1 mole of the aluminum hydroxide solid to form 3 moles of water and 1 mole of aluminum ion. All right, 51, A, B, C, and D would be examples of electron transfer reactions, redox reactions. And in a redox reaction, something is oxidized and something is reduced, right? Oxidation doesn't occur without reduction. So when you're oxidized, you're losing electrons, and when you're reduced, you gain the electrons. So the way we figure this out is by assigning oxidation states to the reactants and the products and figuring out, who gained the electrons, who lost the electrons. So the rule is when you have elements like nitrogen and hydrogen, they haven't lost electrons or gained electrons yet, so they have an oxidation state of 0. Nitrogen and ammonia would have an oxidation state of -3, and hydrogen being less electronegative would have a +1. All right, so 3 plus 1s to 1 -3 gives me ammonia. All right, or you get the sum of the oxidation states being equal. So that's the other rule. All right, so in order for nitrogen to go from a 0 state to a -3 state, it had to take electrons, so it's reduced. In order for hydrogen to go from a 0 state to a plus state, it had to lose electrons, so it's oxidized. That's the language. Iron 2 nitrate reacting with aluminum. Aluminum is going to be a 0 state. Iron 2 is going to be a +2 state. And on the other side, iron is going to elemental iron, so that's going to be a 0 state. And aluminum is going to a +3 state, and that's classic for aluminum, right? It goes from a 0. It's either 0 plus 3 at this point in the course. So when I look at this, the only thing that wasn't involved in this reaction was the nitrate. Nitrate went in the same way it came out, right? There's no change in oxidation state, so it would be a spectator ion if I were doing this. But the change is aluminum going from a +2 to a 0. So in order to do that, it had to gain electrons. It's reduced. And aluminum went from a 0 state to a +3. It had to lose electrons, so it's oxidized. In C, you've got elemental chlorine, which is 0. And you've got sodium iodide going to iodine and sodium chloride. Now sodium has a +1 state on the reactant side and a +1 state on the product side, so it's a spectator here. It's not involved. The change is iodide going from a -1 state to a 0 state. So in order to do that, it had to lose electrons. It was oxidized. And chlorine going from a 0 state to chloride, a -1 state. It had to gain electrons, so it was reduced. If we're looking at D, we got lead 2 sulfide reacting with hydrogen peroxide to form lead 2 sulfate. So right there you can see the lead's not involved in the reaction. It's lead 2 on the one side, lead 2 on the other side. So it's about the sulfur with a -2 state turning into sulfate. Sulfate, if you want to write it on your page, has got you've got a -2 charge on sulfate and 4 oxygens attached to the sulfur. The sum of the oxidation states would have to equal the charge on the sulfate. So the sulfur would have to be a +6. Now with hydrogen peroxide, this is a weirdo for oxygen, right? We always count on oxide being -2. Well, this is an oxide. This is peroxide. So if hydrogen's +1, you only have 2 of them. Each of the oxygens has to be -1. Going to water where you've got a -2 state. So again, you figure out the oxidation state of the sulfate by adding up the sum of the oxidation states to get that +6. So in order to go from a -2 to a +6, this means you were oxidized. You had to lose electrons. And peroxide, going from a -1 state to oxide as a -2 state, you had to gain electrons.